Please give a very warm applause to Stefan Burschka.
Okay. So I'm expected to speak now, right? I didn't expect so many people actually. So it's a great honor for me to be at the Chaos Computer Club conference because it's my first time. I never expected to be here actually, and I'm actually not a hacker. So my formation is physics, and I deal with traffic data. And I also deal with troubleshooting large infrastructures. Large infrastructures is something like 10,000, 20,000 pieces of equipment, router switches, any operating systems, humans in it. So pretty complicated stuff. And when something goes wrong and they don't find the problem, you need to figure out where something happens. And then when you, in that business, you start developing tools for you. One we give open source here, Tranquilizer, hint, hint. And then when I was asked to have this talk here, I said, okay, the people are not miners, the people are hackers, really smart people. So I will talk about listening to packets. So packets are actually something like that, what you see here. So I have my laser pointer here, I can kill you. So this here. And what you need is an ear. Who knows Snoop? Nobody knows? Oh, great, you know, on the Spark 5 or Spark 1. They took this feature out, I guess, but there was a command line switch which routed the traffic to the amplifier and then to the loudspeaker, and you could listen to traffic. And actually you could, your ear is amazing. It does a Fourier transform. Does anybody know that? It's cool, cool stuff. And you are actually inert against noise. And when something happens, whoop, your brain detects it. So the idea is actually to do that with IP traffic as well. And as everybody can do that, I guess, if I play a tune, after a few seconds you know what kind of tune that is. Some people are so good, they identify the singer. So you actually can do that with IP traffic as well. So when I get that idea, there's this poor guy, Benoit Dupasquier. He was a student, master student, so I worked with him on that. And actually, he got for his thesis, he got a science prize at the EPFL, and now he does his PhD in Belfast. So unfortunately, he's not here today. So, but smart guy. So, the contents. Who, what, why, I will tell you who we are, what we are doing, and why we are doing it. I give you a short introduction to traffic mining. Who wants more just comes up to me, and I'll teach you. Then, engineering approach. So we will need some engineering stuff in that, something like transfer functions and stuff. And then, traffic mining signal analysis. But I will keep it simple. There's some math in it, but I will explain it different. I'm a private pilot. I fly gliders. I love flying gliders, so I will explain it with airplanes. And then I will give you some results, and then you can ask me questions. So this is actually the group. Some people are actually here, and yeah, the guy with glasses is clear who that is, and we really stick together. Before we came to this company here, we worked at a great operator, a really big one, and we had some of these loony projects there, and I tried to educate young guys, especially here, Misha and Fabian, to actually go for the moon, to do impossible things. And you won't believe it, these guys can do it. And then the people are 20 or 21, and then they're actually at the university grade. So I educate my own guys, and there's a question mark, that's a hint, we are looking for people. So we're also working with universities, so sometimes I pull people in and I do boot camp. So the people come to me and I make them suffer for 1 week or 2 weeks, and then they can do these things. So if somebody wants to do boot camp, come to us. So what? Network troubleshooting, you need two things. One is to discover the network. A lot of people don't know what the network, what is actually in there, what it's doing. So we did something like Nino, Nina, it's an auto-discovery. Trendalizer, if you're dealing with 1 tera, 10 tera, 20 tera of traffic, you need something that digests that and transfers that into a flow or into that, right? And then we do something like operational pictures, and I had this problem looking at 11 or 20 dimensions. Who can understand here 4 dimensions? I mean, visually. Oh yeah, okay. How do you do that?
Projecting them down in 1 dimension.
Okay, then 6. 6 spatial, 7, 20. Okay, there's Torben Rühl, smart guy, and he's working with us. He's actually from University of Marburg. And these are maps. So what you see here is something like 1 tera of traffic, 10,000 IP addresses in it, and 11 dimensions. And you can identify regions now, 10 regions, and you can see it. It's projected, or 2 dimensions. So, and you can here identify an anomaly. So that's actually the map we want to use. Does anybody know Cajon maps? Okay, that's a total different story. Needs another talk. So if I give a workshop or something, I will explain that to you. Then automatic protocol learning. So you give me traffic, we reverse engineer the state machine of the traffic automatically. Antonio Tofio, master student, did that, also a really smart guy. And this here, that's the next generation protection. Something like evolving an immune system. And as I heard, somebody will do a lightning talk about that sometime, so if you're interested, go there. So, it's Christmas, you see packets whizzing around, so one direction, and here the direction coming back. So what's in it? Can you tell me? How do you guess that? Now I blindfold you. Okay? You're blindfolded. We make it easy. I take packets, and I shift them over the floor. Right? Shift them. And if they're heavy or not, they have the same velocity. So, what is in there? No, you cannot. Privacy, and you're blindfolded, or it's in the tunnel. So I tell you, there are some animals in it, elephants, tigers, so don't open it, you get eaten. Then butterflies, flies, whatever. How do you figure it out? Anybody an idea? You are blindfolded. Timing. What timing? I shift them over the floor. And sound. Yes, smart woman. Sound. But what is sound? Sound? How does this sound is created? Friction. Yes, very smart woman. So, friction. So actually, we convert. Yeah, we have some thermal energy in it, and we listen to it. So what we can guess, it is actually the material of the box, for instance. So when you do some physics, you figure out they're heavier, they stop. So you can hear the time. Yeah? Could you figure out whether they are elephants? Whether they are green or yellow elephants in it? Can you do that? But you know, are there any green or yellow elephants? Are you nuts? They're gray. So you can assume there are no green and yellow elephants in it. right? This is what you do. You have priors. And then you can guess, right? What else? You can look at me. I'm an old guy. You have really sensitive ears. I have to lift the box. You hear the cracking of my bones. The cracking of my bones, right? The more they crack, the louder they crack, the heavier the box. If I tell you there are elephants and there are hamsters in it, from the cracking, you could tell there's an elephant, there's a hamster. But then I'm sinister, I put more hamsters in it. And then you're done. But can I fill a box like that with a lot of hamsters and they have the weight with the elephant? A small elephant, baby elephant. So you get the concept, okay, we can go all drink a beer. Or do you want to hear more? Yeah, okay, good. So, traffic mining. What do we do there is listen. What you did here, listen, see, understand, and find invariants. I will show you what they are. This is the application here, but the important thing is here. So you have down here an IP stack with all its fault and stuff. Here are operating systems. They're all flawless, right? And here are applications, and they are flawless as well. And we are invincible, we are flawless as well. And organizations are flawless as well. Is that right? No, good. So, what we have here, we listen down here. And we guess what's wrong here. Whether there's malware around, whether something is misconfigured. We listen and tell you what kind of application that is, or what kind of user. So you have something like an SSH connection, whether it's you or him. Whether you issued a kill command, or he issued a remove command. And you can even guess something about the organization. But just looking at one packet, not more. That's actually the beginning of boot camp. So, what is possible? What I will not talk today is about SSA command guessing or what you can do in IP tunnels. It's earlier work, it's published, some of it. If somebody is interested, he can come to me. I will guide him to that. We will talk about listening to IP packets in a flow, and it's encrypted. And now the question was, the origin actually was a problem from the feds, and whether you can catch pedophiles when they are communicating encrypted. So people said it's impossible to do that. So when I said, okay, it's impossible, let's try it. So what you do, you take the packets, you have here the time, and you have a feature here, which is a packet length, and which is in the header, IP header. Everybody knows the IP header, right? What's the first byte when I say 47 hex? No, not everybody knows IP, so you have to do bootcamp. So, right. So, and we try to produce an ear, or something like that, or use our brain to interpret that and to answer a question. So, if you start listening to this here, so, yeah, and you end up here, then you're done, because that's encrypted. So if you try now to decrypt it, you can do that. I'm not a cryptologist. People can do that, maybe or maybe not. And here's your 4.5. So it's IP version 4, and has no option, right? And there, here in the blue range, there's some information, and here you cannot do anything. In the end, if you start there, you end like that. Yeah? It's too much effort as well. Is there a simpler method? So I actually said there's no real theory about it, how to do that, and what kind of features are relevant. So when you look at traffic, you can look at the IP header. If you have TCP traffic, you can look at the TCP traffic header, UDP header. There's a lot of information around. There's TTL, there's IP ID. right? Sequence numbers when you have a look in the TCP header, but are they relevant? Are they relevant? Yeah, you're sitting in the front row, sorry. I always take the guys in the front row. You're next. And then I take the second row. Are they relevant? Maybe. We don't know. That was a minor, right? We don't know. So we have to figure out. So there are two ways to figure out that. So you take a lot of data. So let's say you ask the question, one class, second class, third class, and then you put that on a machine, some artificial intelligence, and then you get something like a paper and a paper award or so, but that doesn't mean you understood the problem. So we are interested in understanding the problem. So I thought that's a good picture. So when you have something encrypted, everybody knows here what a tunnel is. Imagine trains. Trains just going in the tunnel. And the question I ask, like with the packets, what kind of train? Where does it go? That's easy. How many passengers? What kind of passengers? Humans, elephants, hamsters, whatsoever. What is the color of the T-shirt? Who sent that packet? Yeah? And the only thing what you can do is listening outside the tunnel. And these train tracks, in the old days, they had this gap for temporal reasons, material expansion, and then you hear these da-dum, da-dum, da-dum. So the velocity, you can hear like da-dum, 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 a slow train, da-dum, da-dum, da-dum. Yeah? And when something is heavy, it's noisier. So that's the only thing what you can do. It's like being blindfolded and only listening. So when you listen to that, and we just say the sound is proportional to the force. So it's not the exact theory, what I'm delivering here. It's something like a motivation. So we look at the force, and the force is this, differential of the impulse, and I guess everybody knows that, everybody went to school, right? So we differentiate that, and we get here the impulse is mass times velocity, so we differentiate that, plus we differentiate that. And the packets on the internet, we assume they have all the same velocity, right? They whiz around with the same velocity. So this is gone. That's nice. So we have this term. So what we do, and now if there's a mathematician here, please look away, because what I'm doing, I just expand with the packet. And packets, they are smooth, right? Okay, they are smooth, really smooth, and expand, and you can differentiate them. And you get two terms. So what is that? The packet per time. Do you know that? Packets per time, packet rate, time. And here, mass per packet. So what is mass, I thought? So mass is something like the length. And this is the packet fire rate. That's actually the interdistance. The machine gun, your IP stacks, fires out the packets. That's so cool. So by thinking, we found out two features. So let's look at them. And then we said, okay, so everybody does HTTP, DNS, all this kind of stuff. And at that time, Skype, undetectable. Skype, really hard problem. And everybody knows Apollo project, John F. Kennedy, we do things because they are hard, right? So we thought, we looked at Google Talk, Zip, that was too easy, so we took Skype. Pour Benoit. So then, there are many undocumented codecs, and there was the Silk at that time, was undocumented, interesting. And so the others, they have a pause sending packets. So you could easily detect when the speaker has a pause. That's so easy, right? We don't do that. We like Skype, which constantly fires that. That's really a really difficult problem. And the Skype guys are really cool. Really love what they did. I mean, they are gorgeous, these guys. Beautiful minds. And then we said, if we know what kind of sentence we have, could we detect which Skype conversation has this sentence in there? And what we do now is what I threatened. I pick one or two, and we do now an exercise. Feature extraction. What do you see? I ask him. What do you see? Yeah, good. Do you have any question? Anybody having a question? Ah, what's the green and what are the blue ones? What's the question? Yeah, very, very good. Okay, so the green ones denote the communication between two peers. The blue ones are out to supernodes. Okay, very good. Now you have information. Next, what do you see here? Anything come to your mind? You? Sorry, you're sitting in the front row. Ah, wavelet. We have to talk. You understand wavelets? See, you're in trouble. The time scale, yeah, but you know, that's just the resolution. That's to confuse you. Okay, go ahead. Ach so, okay, good. I do that, yeah. Next. Hey, listen, I just wait here, yeah? The regularity at the end, he says. So you mean this here or you mean this here? Yeah? Cool guy. Yes, that's the first thing what comes to mind here is that. And you see, this is above 0. When you look at other applications, they have packet length with 0. So the first Skype detector of the very first version, now they are smarter, was minimum packet length equals 3. And Skype was impossible. That's this, and that's the ping. This is very old Skype, right? And here is supernodes. And here, what is that? And what is that here? That is sinister. Why does the packet length go down? Codec, adaptive filters. So you actually could see that this is codec training, trying to figure out how can you optimize the packet sending and receiving. And that was me. And that was Dominic, a student at that time. He had Windows and Linux. At that time, you could just, by the packet length being used for the communication, say which operating system that is, even if it's UDP. TCP is easy, right? But even if it's UDP. So now, this is no different. And this is somebody who talks slow. He had to listen. You see a lot of movements here. And that's the guy who talks a lot. I guess that's me. And so, and then when I saw that, I thought, oh, maybe there's movement. Maybe we can do that, right? So we identified now features, and you guys did now a mining approach by looking at it, not by using some elaborate method, by looking at the data. And that's very important, to look at the data and to understand the data. Very important. So the first thing what you need is a hypothesis. So engineers around, lift your hands. Electrical engineers? Yes, good. So transfer function. The existence of a transfer function of the audio input that comes from you, from the microphone, and the observed IP packet length. So we said there exists a transfer function, but transfer functions are linear. But we said, what the heck? We try that. And then output, the output, what we measure is predictable. And then, given the output, the input can be estimated. That's our strong hypothesis. Okay. Then we have parameters which influence. So that's about understanding what's going on there. So we have basic signals coming on. So they have amplitude, they have a frequency, There will be noise, right? You can do assumptions about it, and there's silence. Because there are people who actually stop sometimes talking. I don't, but there are people normally. So phonemes, there are phonemes. There are people who do language. They do a study about languages. There are phonemes, there are words, and there are sentences. They exist. That's actually the prior. There are no yellow and green elephants. So we already know something. That's very important. The next is, everybody uses Skype. Who uses Skype? Yeah, see, everybody. So, and then, to make things easy at the beginning, we only use UDP communication, only communication between two peers, because it's otherwise so damn difficult enough. So we just started, what I say, simple. And then English. Everybody speaks English. I speak English, everybody. Okay, so that's the basic lab setup. You have two laptops, or you have computers, you have operating systems on them, and they exchange packets. So, you have different speakers. It's not only the same speaker. So, when we have a woman's voice or a male voice, how does this influence the packet length? We don't know. We have to do the experiment. And there was a nice guy who was actually into voice recognition. He had a huge database with different speakers and different sentences in it, a humongous database. So we did the experiment. So we know something about Skype. There's something about Skype to read, so we know there's cryptography in it. We know there's a network layer. We know there are sound cards. We know there's something, different speakers. And we know that there's software in there. So these are things we know. So we could use them against these guys, again with the green and yellow elephants. And then the transfer function. That means you put something in, like a step, and here you have your black box, and you just see something coming out. Does anybody know what kind of filter that is? High pass or low pass? Thank you very much. Yes. We thought, okay, that's so easy, let's try that. Okay, let's try that. Oh, damn. You expect you do first, we did a lot. I mean, we did everything what engineers try to do, and when you expect doing a frequency sweep, you get this. Oh, damn. So there's something really complicated in it. Something that changes per frequency, optimizes. So you could now start looking at the codec. That's actually a smart thing, because they cannot change what the codec does. They can change their program, but they never can change the codec they use. And you have certain requirements for a codec to actually receiving packets. Otherwise, he can't do his adaptive filtering and predicting business anymore. But this here, yeah, it's a bit rising, but it's going like that. So, we did other experiments and figured out in the end that Skype is this. That's our model. Every scientist needs a model, so we said, okay, here come the trains, and here's the codec, and he tries to unload something in the train, and they have different speeds. And when you have different speeds here you have a higher speed, here you have a lower speed, then something of that goes in there, and then something in there, and the next one is empty, and so on. And that somehow explained this behavior. And then we were very content and drank a lot of beer and thing, but it doesn't really solve the problem, right? But it helps. That's our understanding. I know it's wrong, but the cow is round. All animals are round. The first development, So, now, okay, we do serious business. We don't do round cows anymore. We go now serious. We still understood the engineering approach, assuming the system is linear. And we can do everything what engineers do in order to understand that didn't work so much. So, So, okay, we need something more with more juice. So it needs to be learned. It needs to be learned. So The task is, again, you listen to this here. These are the packet lengths. And you know you have phonemes in it. Everybody uses words. Everybody uses sentences. So we somehow need to find a mapping. Okay. And we need to produce invariants. An invariant is something that does not change when you change the environment. So when you have different speakers, when you have a different Skype version, when you use something else as an encryption, it does not change, right? It's something like when I say animal, you come up, what doesn't change by an animal? No, you sit in the front row, sorry. Animal, if you have to characterize an animal and a human, what's the first difference? You're blind, no, you're not blindfolded, you can look at it, but you may not listen. Yeah, you could. Easier, think simple. How about looking at the legs? Yeah, we take many animals. We take hamsters, we take elephants, we take giraffes, we take dinosaurs. They died out, but you know, they had 4 legs, some of them. So you get something like a 98% probability that when you look at the legs, and they are 4 and 2, then, okay, that's a human, that's an animal. And then you meet a cephaloraptor, and then you're fucked, right? But he died out, so yeah, but you know, it's a probability. So it's a good feature. And not if you live many million years, something like 65 or 100 million years ago, but we don't. So we have to produce something like that. So, we looked at the phoneme. We had the phoneme database. So, z, pleasure, right? Z. And that's the signal here. So we have 44 phonemes. In order to prove that, we have to prove this, a mapping, a homomorphism, yeah? That this is here valid. And that's a tremendous lot of work, but we did it, and we figured out we didn't find anything except for the signal length and silence. So signal to silence. So people will think it's trivial, but estimating when you have silence, because it changes, is not trivial. But I said, okay, let's use that. Then word construction, when you take a very simple approach, and we like to do a simple approach at the beginning, is not easy as well. Then noise silence estimation. When you can estimate that is silent, and that's a signal, if you don't do that, you're done. So you have to estimate silence. And the longer the sequence, the better the results. So the longer somebody talks, like me, the better the results. If somebody talks only 2, 3 words, very difficult. So we decided sentence detection. We do simple things, sentence detection. Here you have a sentence. Yeah, it's a really silly sentence, like the frog prevents them from arriving on time. Anybody flying with planes here? Yeah, so this happens. So that's actually the sentence. So we saw same sentence, similar output. Not same, similar. So we have a chance with some statistical means, and that's very good news. Here we have different sentences. Yeah? I put a bomb in a train. Yeah, I don't know where I get this sentence from. And the thinker is a famous sculpture. And you know, sometimes we talk bullshit here. So you see it here. So you can see with the naked eye, there are differences. And when you look at that, what do you see? Is there something you recognize, a feature in both signals? Bit louder? Yes, absolutely. Yeah? So by looking at it, you have to look at the data and you see similarities. You see here and here. Yeah? Good. And what you see here is actually they have different lengths. How do you deal with different lengths? Oh, damn. So we needed something that can compare signals with different lengths. So how do you do that? Yeah, there's something like hidden Markov models. So we thought, well, okay, but well, too complicated. Well, let's do something easier, dynamic time warping. And that actually takes one signal and the signal, and now maps them onto each other in time. So you see here 1 point correlates to 2 points and tries to find an optimal path, expands one signal, compresses one signal, and tries to figure out an optimal path, and then gives out a number and says, these signals are so comparable. So here we see 2 signals, and what you see here, this blue means very, very similar, actually the same. And the red areas, so if you compare this here to that, or this here to that, so this here to anywhere, to dissimilar, it's dissimilar, so it's red. And what you do is actually, you compare 2 values and do something like an Euclidean difference. So between 2 vectors, you have 2 vectors, and here is the angle, and when the angle is like that, it's different. When the angle is 0, it's almost the same. Right. So, with 2 signals which are very different, so we have 2 sentences, very different, you see, are all red. And that would be the optimal path, but no way, they're different. So we have a means, actually, to figure out which signals are the same and which signals are not. So if we know the sentence, we could create a model, and then we could compare it to all Skype conversations and then figure out where is a similar signal that should have this meaning. But now there's a problem. What's the problem? Thank you very much. Absolutely, different speakers. So what you do with that? Oh, damn. So, it's speaker dependent. So we figured out we can do, in the average, 66%. That doesn't sound much, but actually, if you can do that, you're pretty good. And when we had 83 correct guesses under certain assumptions, right? So, but different speakers, how do you deal with that? Engineering, Kalman filters. Does anybody know? I love Kalman filters because it's from the 60s. I'm an old guy, right? They are really cool. Yeah? So they actually are able, you can measure something, even if it has a control input, like an airplane, and then you can estimate what's the next expected sample. So this can average. From many speakers, it can produce a model of a signal which is correct for all speakers. And it works repetitively, and these are all complicated matrices and stuff, but you can do an assumption, and then you make all these things constant, and then it's pretty easy. So if somebody has questions, when somebody has questions, you can come to me. But now, I promised you, I explain you Kalman filters, so we do it with airplanes. So imagine you're somebody, radar guy in the old days, and you want to track a plane. And you have here Bob and Alice, and you guys, you're cryptologist guys, there's Bob and Alice, and you get from them points in time and space. These points. And they are noisy. They are not reliable. Both are not reliable. And you get from them data. And you have to trust them or not trust them. You have to decide whether I trust them. And these are these 2 independent speakers. And now you have to estimate the next reliable position of the plane without knowing anything. If you have a theory about it, how a plane flies, it helps. But if you don't know anything, it's actually our task. We have from independent speakers unreliable information, which is noisy, where we do not know how this signal is actually produced, by the IP stack, by everything what's in there, right? It's the same situation. This is what Kalman filters do. You get unreliable information in, you produce the next good estimate, like an average. It's not correct, but it's a good guess. Not everything is correct in here, but I guess that's what it does. So we have here an example. It's actually from a tutorial from somebody else. Here, we estimate this constant line. And here you see the Kalman filter. Here we have all these unreliable points. And now this thing, if you tune the parameters right, and it learns that. And you can feed that all kinds of crap, but it will learn to follow that line. So if this line is changing, what happens then? Here we are. Here we have now many speakers, these different colors, and the Kalman filter is the blue here. And you see, here the speakers, the signals change. And this Kalman filter learns, oh yeah, this is crap, I don't trust it, I just go through. It adapts its average. And when something really drastically changes and everybody agrees, it follows as well. This is how you produce a model of independent speakers. That's a problem. Did anybody see that? Did you see that? I had time and now I have packet number here. Hey, come on, you have to listen. Or did you drink too much beer yesterday? I mean, you have to see, that's packet number. What's wrong here? Yeah? And? Yeah, it's a difference in speaking speech. What do you mean? What's wrong here? Different, yeah, but packet number. Packet 1. When does packet 1 and packet 2 come? What did I say about packet interdistance? Yes, one thing. But I could take care of it. I have methods. But what else? Oh, sorry, the sequence might be wrong. Yeah? But there's information in the packets. I could take care of it. So you mean the difference in time? Yes, absolutely. So this packet could come a second later. Okay, we know that in Skype wouldn't happen, right? Something like 20, 30 milliseconds or so. But here we use the packet number, not the time. And I did this calculation there, and it says time difference, and I used the packet number. Why did it work? Thank you very much. Somebody is listening here. Okay, so that's why it works. And that's about science. You have to be honest. Oh, sorry. I said it beforehand that Skype has something like a constant packet rate, 20, 30 milliseconds. So that's why it worked with the packet number. And it makes things easier. So you assume these packets coming in constant times. And that can be wrong, because there are signals who do not do that. And with Skype, it works. But if you use time, right, and if you use more pre-processing, right, invest more work, you go higher than 83%, and you go on average higher than 66%. Yeah? So that's an important issue. So mitigation techniques. It's no perfect solution. So if somebody wants to do an encrypted communication, he always has a trade-off between performance and computational power. And this is what these Skype guys did. And they did amazing work. I mean, it's really cool. Then, yeah, you can do padding. You can give me all packets have the same size. Absolutely. And you can influence the IP stack. You can do queuing. They come with the same rate. But be careful with padding. We found a function in an IPsec tunnel, and we produced a function which uses the padding against you. And then we can do the job as well. So do it right with the padding. Or you could add random payload as well. Random packets, randomize it. right? But it's computationally expensive. But mitigation, for you guys, easy. So, conclusions. We could, under specific, ideal situation, as in the lab, we could reach 83%. More elaborate effort, you can go higher. Speaker-independent methods, Kalman filter. And there are people who are afraid of Kalman filters, and they come hidden Markov models. And somebody asked me, why didn't you use hidden Markov models? And I said, you know, I didn't know. So I tried something that I know, and I'm old, I'm sorry. So then mitigation techniques, as I said, for you guys relatively easy. And there was a paper in 2011, and they did that, and they produced reasonable results. And now here we come. And here I come to my final slide. So don't be afraid, you know, I stop talking then. What you see here, there are signals. And here you see a gap. So if you take the packet, you do something wrong, you distort the signal. And that actually looks like, so what do? Do you put zeros in here? Can you do that? And how do you sample this signal? There's something like Shen. Who knows Shen theory? Yeah, very good, very good. So, so how do you do that? And there are methodologies. And then we come up with something like that. That looks really silly, but that's something like an average which tries to estimate how much of this signal is relevant for me. And to produce something like a cutoff frequency, and then I have this signal, and this signal I can sample with twice the frequency, and then I can do my signal processing on it. And then I'm honest. I don't use packets. Yeah? I try to do the thing right. Because there are a lot. This is, for instance, an HTTP connection, a complicated one. And if you want to do some mining and some guessing with signals on that, you have to do that job. Right? Right. So, what I try to convey is actually this. He's unfortunately good. All the good guys are dead. I mean, Einstein is dead, Carl Sagan is dead. I feel really bad now. So you have these, science is a way of thinking. And this is what I try to teach. It's not applying methodologies. It's not knowing everything about AI. It's not about hacking somewhere. It's about seeing. It's about understanding. Yeah? And it's not about knowledge. It's the thinking what needs to be adapted. And the open source tool we deliver, which actually does the pre-processing for that as well, and which is very useful for network guys. Today I uploaded the version 0.57, so on SourceForge, if somebody is interested giving us feedback, because I see a lot of downloads since 1.5 years, but nobody talks to us and said, okay, that's crap, or this is crap. So if you mind, yeah, diss me or just try it out. And you see here this 9th anteater and all these ants, really cute. It's actually here in the back. Yeah? So we might produce t-shirts sometime. So if you test it or if you use it, you get a t-shirt maybe. Right, so that's it. This is my email address. It was a pleasure. Go, ask me questions.
Questions? No questions? I don't believe you.
I mean, if somebody wants to know more, just come to me, ask anything.
We have a question back here. Wait a moment.
So somebody has a question.
Hi, I just wanted to know what your job is at RUAG, which is a Swiss defense company.
Yeah, I have to kill you if I tell you. Now, it's aeronautical and space, and I'm a pilot, and I always wanted to work for an aeronautical and space company. But one of the jobs is this, traffic mining and producing tools. And we even give something open source. Is that cool? Yeah? I mean, it was developed at the company before, but they told us we can give it open source, and we give it back to the companies, we give it back to the community. That's it. But now you're a target.
Any more questions?
Hi. I really don't know how Skype works, but
Do you
If-
think I know?
if the encryption use CBC, I don't understand how you can see something or hear something with that.
Okay, there's a guy for boot camp. So, okay, what I try to convey is I do not decrypt. I just take the packet length, right? So you send packets. No, not you. Skype sends packets. And I take the packet length as a signal, and that's it. And I just used it as a metaphor to listening to that. It's a signal. It's like I'm talking to you. You listen to the signal. And now we are building tools which do the same process. It's not like that I'm listening on the wire. And I'm
No, really, yeah, I understand that, but you are like trying to see patterns on something that that must be like random.
But it isn't. The idea is not the content. You speak of the content. I do not look in the content.
So you can see patterns on encrypted data.
No, on the packet length,
So
not in the content.
Think about the trains. You don't know what's in the trains, but from the boop, 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 boop within the tunnel, you can estimate
that.
if the train is fully loaded or
Or not.
empty, for example. And that is what he uses.
Okay, thank you.
Okay? Otherwise, come. Next one? No, everybody is leaving.
Can you guess the sex of the speaker?
Yes.
He can even tell you what kind of underwear the speaker is
Yep.
wearing. No kidding.
Hello, another question. Now, what would you do to make Skype more secure now that you know the
I
attack?
told you.
Yeah, I know, but let's say if I would play an audiobook in the background, would it more or less keep me secure, no? On a sound level? Very
If the
basic.
sound level is really high, yes. I mean, I said under ideal condition, and the ideal condition is you speak, nobody else is speaking. That's it. So what your ear and brain is doing, right? This is what we cannot do. But that's actually an interesting question. Thank you very
Because
much.
it's very easy, no?
Thank you very much.
Let's rotate audiobooks in the background, or let's put the audiobooks inside afterwards.
Absolutely. Absolutely.
And you could also say the same audiobooks are a private key for two people to communicate securely.
Yes. Yeah, that's another thing. So you can add it to that. Thank you. I mean, we just thought something simple, right? Yeah.
More questions.
Did you ever try a real learner, like who's capable of time series analysis?
Yes. Yes. We didn't do that because we wanted to show you can do it even by looking at it very simple. If you use these, you get higher precision and recall. Absolutely.
Last question.
Sorry, how you deal with non-native speakers that are doing mistakes on building the sentences?
We didn't.
Okay.
These are these assumptions. I should have said that. That's my fault.
Everyone
Thank
who
you.
has more questions can meet Stefan outside of the hall
Yeah,
and
I mean,
talk
you
a little
see
bit to him, okay?
Fertilizer T-shirt.
Thank you.
Thank you.
Okay.